With no further ado, please put your hands together, and we're going to hear a lot about how you can potentially, how can you have an X-ray machine at home, essentially, and what kind of techniques can you use to utilize them. So please put your hands together, and let's welcome AleksandarNikolic and TravisGoodspeed.
Howdy, folks. Quick show of hands. Who wants an X-ray of their own? Okay, we got the right audience. This is AleksandarNikolic. If you're not familiar with his work, you should be reading more about his articles in reverse engineering. He's got a great one in here about figuring out the calling conventions for Windows functions by looking at the control flow guard definitions and hashes of them, and then brute forcing his way backward.
Travis probably needs a little introduction in this crowd. You're probably all familiar with his previous projects that involve radio reverse engineering, microchip decapping, ROM extraction, and so forth.
Cool. All right, so I have this disease late at night that involves alcohol and eBay.com. And occasionally you see these machines pop up on eBay. This is a Faxitron DX50. This particular auction that is for $100 has a broken Roentgen tube. So do not imagine that you'll be able to get all of this working for $100. But you can definitely do it for around $1,000 or less.
And this auction is currently live, so.
Yeah, it'd be kind of cool if we sold this by the end. Just realize that this is missing both a digital camera plate and a Roentgen tube. So if you can replace the tube, you can use this as shielding in order to make film photographs, but you will not be taking digital photographs in this. There is the whole race thing in that if you buy it on your phone in the lecture, you don't have time to see the lecture yet to know what you can repair and what you can't. This is what the machine looks like. I've got 3 of these things. Alex has 1. This is not like a dental X-ray. This is a biopsy X-ray, meaning that you open that circular door in the middle there. That's thick steel so that we don't get cancer, because cancer is bad. Fuck cancer. You then place your sample inside, and a computer can then order a Roentgen tube, which is a vacuum tube that produces X-rays, at the top of the machine, to fire those X-rays through the chamber to a sensor on the bottom of the machine, which by USB will provide an image to your computer.
So these machines are, these X-ray machines are called cabinet X-ray machines because they're self-contained, which makes them safer to use in general. There's a couple of different models that are popular for this sort of work.
The X-ray emitter is controlled over an old-fashioned 9-pin serial port. It's also got like a control panel on the front for changing the voltage and for firing the X-ray gun. If you wanted to make this self-contained, you could actually replace that serial port with just a microcontroller to run the gun when the start button is pushed. It might be handy if you wanted it to run, say, inside of a dark room without a computer controlling it. The digital sensor, and a large part of this lecture is about how expensive these digital sensors are. It connects by USB, and in 2 of my machines, the sensor had been harvested before it was sold on eBay. So I got the machine, but I could not take X-rays because I had no digital sensor.
One note with one feature that makes these machines desirable when it comes to electronics reverse engineering is that they have a point source of X-rays, which gives you nice and crisp, high-resolution images.
Now, X-rays are kind of like light, but they're not light. So you do not have a lensing effect on them, which means that you are not able to reduce the image to fit on the image sensor. If I were taking a photograph of all of you with my phone, the phone's camera element is very small. And the phone has a lens on it, and the lens gathers the light from all of the angles that come in from the room to point at just that sensor in order to keep it small, and by keeping it small, we can keep it cheap. Because X-rays do not have this effect, The smallest you can make the X-ray is a 1-to-1 ratio with the original source, which means that if I want a 2-inch by 2-inch photograph, I need a 2-inch by 2-inch sensor, which means I need a 2-inch by 2-inch microchip, which is a massive amount of space to put on that wafer as they're manufacturing it. And that's what keeps the price of the digital sensors up, and that's why my eBay seller robbed me in my first 2 units. Now, the good news is that, like many of my projects, John McMaster already played with this machine, and he wrote an excellent open source client library for the Faxitron DX50. It's a Python script that fires the gun, it processes the image. On my desktop, I just type make X-ray, and I get a digital photograph the size of my sensor. The sensor itself fits here in the center of the chamber near the scary radioactivity warning sticker. That black hole is transparent to X-rays, and beneath that is where the sensor sits in the normal configuration. All right, so what do we want to take pictures of? If any of you are squeamish about biological photos, if you could please cover your eyes before the next slide. All right, you've been warned. So this is Mickey. We now call him Steamboat Willie because it's legal. And I live in an old house. I caught him trying to rob my kitchen. We had an altercation. Through the X-ray, you can see that the mouse's spine was not broken, that the mousetrap actually worked by compressing the mouse so that it was unable to breathe. So you can do failure analysis on things as well as... fountain pens always look awesome. I don't have a good reason for this, but they look... It's just sweet to see how the springs work, you know, the angle of the nib. You can do it for mechanical failure analysis. So, like I said, I've got an old house. I got an old garage door opener. The garage door opener had like a keychain remote that I really wanted to use with my motorcycle because I've not yet learned that it's bad to wreck motorcycles. And the switch on the left stopped working. And the problem with it was that there's like a little metal leaf that deforms as you press the button in order to make contact. And that had rusted in the middle in order to prevent the movement. So as much as you pressed it, it would never open the garage. I swapped it for the equivalent part on the right, and you can see like a little gap in the bubble of the spring just beneath the button. That made it work again. I also have this problem with, I decapsulate a lot of microchips to photograph them for ROM recovery, as I spoke about last year at ShmooCon. When I do this with dual inline packages, they are gigantic. There's a whole lot of acid required to boil away this package in its entirety. But as you can see from the X-ray, the actual die is on that little square in the center. And the square in the center is metal. That's part of the lead frame. The die is actually smaller than that. So what I would like to do is to take my bandsaw and saw off the sides of the chip, leaving only the middle, so that I have less acid to use, less time in the chemistry lab, can burn through it faster. So I just soldered it to a board, ran it through my bandsaw, and then X-rayed it again in order to see exactly how close I was to being too far. And by doing this, I can then know that next time I can be a little bit closer. You can also do it with like a different exposure in order to see the squaring more cleanly. For potting, sometimes you're trying to attack a microcontroller. The microcontroller is inside of a whole bunch of gobbledygook glue, as in the case of this HID card reader. So this HID card reader has a PIC-18 microcontroller in it. And Milos Mariak has this paper out where he points out that the readout protection on this chip is unique to every bank of memory. And the chip has something like 19 banks of memory. So if you erase the first bank of memory, which does not contain any secrets worth caring about, you can replace it with code that will dump all of the other banks of memory. And those other banks of memory contain the 3 DES keys unique to that HID I-class installation, and you can then use them to counterfeit cards. So when I've got this giant card reader, I want to know where the microchip is in it. I know that the 6 pins on the left are the programming pins. And from Miloš's paper, I know that they're slightly out of the standard order. 2 of the pins are swapped. But I don't know where the microchip is. So I can X-ray them. This is a digital X-ray. And in the digital X-ray, you probably don't know what you're looking at relative to the last picture. If I flip between them, this is the whole image, this is the shortened one. It's hard for you to tell. And if you really look close, you can see that 0.1-inch header in the middle, the big green one. You can kind of see that on the other display. And then you can follow to the 6-pin header in the northwest. So if you look at the 6-pin header, you can see that it's also here. But I'm only looking at that one little area in the center of this device. And if I'm studying this as an individual engineer, I can take multiple photographs and I can arrange them. I can do one of those like murder mystery solver board thingies like the schizophrenics do. But it's really bad for writing a paper or for explaining this. And I need to explain this in a book that I'm writing. So I need a bigger image. One option would be a bigger digital sensor. Unfortunately, that would cost more than my car. So an alternative, and the purpose of this lecture today, is to do it on film. And on film, I can photograph the entire thing, and you can see the RFID antenna around the perimeter. And this is the exact same size as the original, so I can do one on the left page of my book and another on the right page of my book, and everything is groovy.
So this previous image is a result that you get, but with a bit of refinement of the method, you can. Our goal here is to show higher fidelity and high resolution results.
Yes, and this particular sample is difficult because it rises above the film itself, so there's a bit of a parallax effect. And I'm using a flatbed scanner here. By the end of the lecture, we're going to have much cleaner photographs than this one. Car keys are also fun. I took my X-ray machine to my local pub, and people started putting their car keys into it in order to see the microchips. And there are all sorts of things like microchips around you that you don't see in your day-to-day life, because we went from a period like the 80s where we were all going to learn how to program in order to manage our recipes, to the 2020s when no one knows how anything works and it might as well be magic. You know where to touch the phone, but you don't know the mechanism beneath it. And as reverse engineers, our job is to disrespect those boundaries and to dig in to understand how these things work. Thank you. Credit cards work too. This is like a modern chip and pin card with the wireless reading thingy that the kids do at the coffee houses when they're taking forever to pick a latte. And you can see that the antenna kind of coils up beneath the reading point, which I didn't expect. I thought that it would run around the perimeter like the older ones do. This is a continuous glucose monitor. I published a remote code execution exploit for this with Axel April. You can tap your phone to it and then rewrite its non-volatile memory. This is really handy if you buy them from one country and you want to use them with a reader from another country, or if you want to use them past their 14-day limit. They've, of course, closed this bug, so that no longer works. But it's really cool to see, on the image on the left, you really can't tell where the microchip is. You can kind of see the battery on the far western side, and you can see the sensor on the south of the device. But in the northeast, there's a QFN chip. And in light, you can't see that without breaking open the case. But in X-ray, it is very cleanly there, and you know exactly where it is. And if you had to drill through a piece of this case, let's say that I wanted to drill one hole to expose the chip, but I did not want to damage the sensor or in any way break the device, the X-ray would tell me exactly where to drill. So going back to eBay, I bought one of these things on eBay. I'm really excited. I'm getting my first X-ray machine. I set it up on my desk, and I plug the serial port in, and I run McMaster software, and I tell it to raise the gun up to 35,000 volts, and it does, and I'm really excited. and then I run the command to take a picture, and USB device not found. So I open the thing up, break through all of these scary state of Arizona, nuclear control, blah, 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 stickers, and I find that the digital sensor has been removed, and the USB port on this device is an extension cord that runs to nothing. So what do? I buy another from the same vendor. And it has the same problem. So I'm really bummed out. I call two people. I first call Alex up, and I'm like, hey man, you know film. Can we make film with this? Can we expose a picture? Like, how does that work? What did you say?
Yeah, of course. I had a couple of ideas that we could try immediately.
He was actually a lot less optimistic. His response was something like, fuck if I know, but we'll try. When you get a biological x-ray, like when I was a kid, I broke my arm, going to the doctor for that. The x-ray tech back then used film, and he didn't want to irradiate my arm. Like, I mean, he had to, because that was his job, but he didn't want to make it fall off or use too much radiation. So in biological x-rays, to reduce the amount of radiation that you are exposed to, they have this neat little film that receives the x-rays, and then it re-emits green light. And the film that you're developing is mostly not developed by the x-ray itself. It's developed by this, what's the name of the?
The intensifying screens.
Yeah, the intensifying screen. So the intensifying screen is in a cartridge, and you fold the film into the cartridge, and then you bombard it with x-rays. And wherever the x-rays hit, it glows.
In other words, the film itself is sensitive to green light, not the x-rays themselves. So you're exposing the film to green light, which the intensifying screen fluoresces when it's hit with x-rays.
So we bought some of those intensifying screens. We bought the cartridges that the film goes in. We bought x-ray film. He brought regular film. He drove out to Tennessee from Texas, which I really appreciate, because Texas is our only colony. And yeah, he shows up, we spend a couple of days, he converts one of my bathrooms into a dark room, and we figured out how to do film, and that's the rest of this lecture.
One small note on these machines, if you actually want to test if it works, if it's producing x-rays, you put a Geiger counter in it, turn it on, and if it starts going crazy, you have a working machine.
The first time I ran it, I forgot that I put my Geiger counter in, and then I ran a test, and you know, the gun turns on and the radiation starts flowing, and the Geiger counter starts screaming like a stuck pig, and I'm wondering, like, I didn't think that this thing had sound effects. Like, why is it beeping?
Yeah.
We'll swap up.
Yeah. Cool. So we're back to the machine itself. Unlike with the digital sensor, which limits your size, if you want to use film in this machine, you're only limited by the size of the film that you have and the size of the chamber. Rather, the size of the film that you can fit in the chamber and the object that can fit inside. So yeah, the machine has a hole where the hole shouldn't be. We want to put a piece of film there and image it. We know that this is how people have done X-ray films for the longest time. We want to replicate this with film and with currently available supplies, chemicals, and so on. So here's what you need in terms of supplies. We've known that it's possible to develop film on your own, but people usually think that it's an immensely complicated procedure, it requires some precision, and so on. One of the goals here is to show you that it's relatively straightforward. So on the supply side, you need film. In this case, we're using a large format black and white film, which is a standard size of 4 by 5 inches. The film of choice is Ilford Ordo Plus, which has a nice feature that it's not sensitive to red light, so you can handle it under safe light in a dark room relatively easily. and inspect your results without destroying the film. Second thing you need is a developer. This is a simple chemical choice developer of mine is HC110, which is widely available everywhere and shelf stable, so you never run out. And the final thing is a fixer. All the fixers basically do the same thing. Just in this example, we're using Ilford Rapid Fix, but these are, again, you can easily buy them in any well-supplied photography store.
So a quick note on these. These are basically the same chemicals that you would use for developing black and white photographs. And black and white photography is done by a lot of photography hobbyists because it is the easiest thing to develop. You don't have any of the complications of color here. And this is the same thing that high school students would be taught to do back in the days before digital cameras and smartphones. And the proportions that you need here are very generous. So each of these chemical bottles is sold as a concentrate. And when you are mixing it with just regular tap water in order to produce your baths for developing, you'll worry like, oh, do I have too much? Do I have not enough? And the ratios are obscenely generous. It's like you can mix the developer either 1 part concentrate to 15 parts water, or 1 part concentrate to 31 parts water, and it doesn't really matter which. It does have an effect on the film, but it's not going to be the difference between success and failure.
Yeah, you will get a result no matter what. And this is not a pipettes and graduated cylinders type of deal. You just mix them up with measuring cups that you use in the kitchen, basically. It's not that sensitive to the details. Besides the supplies, you need some basic equipment. If you have a dark room or a very dark closet, you can do this in the dark in that place with some developing trays. Alternatively, you can get these film changing bags, which look like a reverse t-shirt. There's a zipper on them. You put stuff in, zip them up, and that keeps the things inside light safe from light. And you just put your hands through it and manipulate the things inside. Besides that, you need a development tank or trays. Here, the photo shows one example, but they come in many shapes and sizes. And finally, we need a film holder, which in this case is custom. Regular 4x5 film holders are made for large format cameras, have metal dark slides on them, and we can't use them directly because that would attenuate X-rays too much. So we need to make an improvised slide holder. Alternatively to this, you can just use an opaque plastic bag. You just need to be careful to use one that's made out of material that doesn't attenuate X-rays. So this is my solution to it, just a 3D printed holder that's held light tight with simple clips, and that does the trick.
Yeah, I've been using an opaque plastic bag, and I just put the film in the bag, and then I fold it over, hold it with gaffer tape, and set my sample on top. As far as the darkroom goes, it needs to be dark, but it does not need to be like sealed against any possible incident of light. There's a crack beneath the door on mine. I'm just using like an extra bathroom beneath the staircase that doesn't have a window. And I won't use it during the brightest part of the day, but if I shut off the lights in the adjoining rooms, I can use it at night, and I don't even bother sealing the strip beneath the door or anything like that.
Yeah. Coincidentally, the bags that the film itself comes in serve the purpose of doing this. So when it comes to exposure time, it's not obvious how you determine the length of exposure that you need. And as Travis mentioned earlier, an imperative in radiography is to limit the patient dose. In this case, since we're imaging things that are already, that are inanimate objects, we don't care about that. We care about the finished result, the highest resolution, the highest detail achieved. So we can forego the intensifying screens, the filters that are usually used. X-ray film itself is made to be, it's coated on both sides with emulsion to make it faster and more sensitive, which all of these things reduce the resolution that you get in the end, and we can forego them for fine grain film, which will require longer exposures, but will give us best results.
And the exposure is under computer control. So you're going to have a Python script. The Python script is going to say, hey, machine, let's do 35 kilovolts. Hey, machine, I want you to fire the gun for 1 minute, 20 seconds, and then return.
And when it comes to controlling the X-ray machine itself, you're controlling two parameters, basically. One is the X-ray energy, or kilovolts peak. The energies of X-rays are on a spectrum, and the kilovolts peak kind of tells you which is the highest energy you're getting. And the other is tube current, which equates to exposure time in this case. Through some through some testing, we've come up with rules of thumb when it comes to exposures of this particular film. There's no benefit to reducing the max energies of the X-rays. 35 kilovolts peak is already at the edge of what's practically usable for imaging boards. And the ballpark for the exposure time is measured in minutes. So this is a lot of exposure, which is not ideal, but so it goes. With the kind of preface out of the way, I wanted to guide us through a step-by-step process of actually getting a black and white film exposed to X-rays and developing an X-ray image, just to kind of present that it's actually easy to pull off. First thing you need to do is prepare the chemicals. As Travis already said, these are not super sensitive to ratios. These are kind of standard ratios that are used in developing regular film, like 35 millimeter film and so on. HC110 has this thing called dilution B, which is 1 to 31 ratio of developer to water, which is 1 part developer to 31 parts of water, and you just need enough of it. This 1 bottle of developer lasts years to me. Fixer, similarly, you mix it in the specified ratio, and if you're doing professional film development, you also use a stop bath and a rinse bath and a couple of other chemicals, but plain water does the trick for us. Step 2, after preparing the chemicals, is to prepare the slide for exposure. You load the changing bag, or do this in the dark room. Again, film is sensitive to light, so you must not expose it to light. You need to prepare it properly. So into the bag go a pack of film, a film holder, and holder clips to shut the holder light tight. You just load 1 sheet of film from the pack into the holder, and in the end you get this nice package which keeps your film sheet safe from light, but is transparent to X-rays, and you can actually expose it. Next step is to actually prepare for exposure. You load the machine like you would in case you're doing a digital photo. You line up the film holder inside the machine and lay the object on top of it. You want to try to make the object lay as flat as possible, or as parallel to the film as possible, to get the best results, but sometimes you can't avoid kind of having it skewed.
Yeah, the X-rays are not coming straight down like a laser. Instead, they're kind of radiating out from a point source near the top. So you will have a parallax effect that becomes more severe as the device lifts further off of the film. The closer you get it to the film, the better your photographs will be. I have perfect photographs of things that are nearly flat, and I have really janky photographs of things that, because of their height, need to sit a little bit above the film.
Next step is the exposure itself. Unlike in the case of using a digital sensor, we control the machine directly here with the x-ray.py script from McMaster's repository. You set the time, and the machine confirms. You set the kilovolts peak, and then you just issue a fun command called fire, and the machine starts generating x-rays. And at the end of that, it issues an audible confirmation that it's done, and your exposure is complete.
It kind of feels like piloting a spaceship when the lights start changing and then the beep fires and it has multiple lockout lights for different safety mechanisms to make sure that it warms up, that the door is shut, that sort of stuff.
Yeah, and the machine the sound that the machine is making actually changes while it's producing X-rays, so you can kind of tell that it's doing something. Next step, after the exposure, you need to safely transfer the film into a development tank so you can pour in the chemicals and develop it. So again, into the bag or in your darkroom, you take the film from the slide holder, you put it in your development tank, and the development tank keeps it light tight, light safe, so you can turn on the lights and continue the rest of the development in broad daylight, which makes things simpler. Alternatively, in the darkroom, you do the next steps under safe light. The development itself, this is a standard procedure. You need to develop, rinse, fix, and then dry the film. The development is, again, there's many prescribed recipes for it. The times are, in this case, since we're using film outside of its standard parameters, all the standard manufacturer recommendations kind of go out of the, are not super useful, so you can use these ballpark figures. You develop it by pouring in the developer into the development tank. You develop it for 6 minutes, jostling the tank every once in a while to keep the developer replenished. Once the time is out, you pour out the developer and pour in the water. The water stops the development. You pour out the water and replace it with the fixer, and then fix it for the prescribed amount of time, kind of repeating the same process of jostling the tank and so on. Once a certain amount of time in the fixer has passed, the film is no longer sensitive to light, so you can kind of open it up and inspect it and see if you need to do something else, some additional processing or not. Finally, you rinse it with water to wash out the fixer. And I should add, both the developer is generally a single-shot developer, so you throw it out after one development. But in this case, you can reuse it multiple times because we're only developing one sheet of film, and you can kind of get away with reusing it. The fixer itself is reusable many, many times, so it's really economical in that sense.
I did not know that I was supposed to be throwing away my developer.
It turns color, so you would know if it's,
oh, okay.
You would know
Right.
not to use it when it turns bad. As a final step, you hang these out to dry and wait a couple of hours until they're completely dry. Otherwise, the emulsion itself is sticky and you can damage it easily.
And they look dry long before they are dry. I have these like light boxes that I set them on to display them, and I have to remember to wait until morning to do that.
Once you have them dried, you need there's a couple of ways to digitize these. You can kind of inspect them on the light boxes themselves and see the results that you're interested in, but in general, you'd want to digitize them and have them in a computer so you can look at them at higher magnification and so on. One way is to use a scanner, a regular copy scanner. Some of the higher end models have support for scanning transparencies, such as film. In this screenshot, we show one that does 4x5 film. Alternative to that is to use a regular digital camera on a copy stand, just pointed at the film. And this will probably give you the sharpest results. And most latitude in kind of manipulating the image or post-processing the image afterwards.
For just viewing your slides, you can kind of see it if you put it on top of white paper. Better than that, on eBay you can buy antique X-ray viewer panels. So I've got a few of these from like old dentist offices and old doctor's offices sitting around my house. Another thing that you can get are backlit LED panels which are intended for artists to do tracing. They produce a nice clean white light, you set the film on it, and everything pops right through.
Next we'll go through a couple of examples of the results that we get from this method. This one.
Yeah, so this one, I still have the film and I'm still expecting a good scan of this, but this particular one is taken by a flatbed scanner with nothing special. Like I just set this on the scanner. The light is coming up from the camera strip side. You'll note that it's a bit blurry and a little bit out of focus, and the film is providing a better image than I'm getting here. So in order to improve these results, I'm going to instead photograph this on a light table to improve the quality. If we jump forward one, this is an example that Alex took and properly digitized. And if you zoom in on this, there's all sorts of precision and detail here that you would not see in the previous slide.
This one is a full size of the film image, so the device that's being imaged here kind of fits over the whole sheet of film, and this kind of shows the size that you can get. Additionally, this image shows kind of the dynamic range that you get with film, where you can see the completely opaque parts where the screws are in this device. You can see the traces of PCBs or wires, the battery holder, and as well on the lighter side, you can see the plastic case of it, of the device, which can kind of help you if you're trying to open it up. Here's another example done with the same procedure, a little bit more contrasty image, better result because this board is completely exposed. It's not encased in plastic. This is a DEF CON badge from 2022, just as an example. Has this interesting pattern on it for capacitive touch buttons. Here's an example of something that's more challenging to image. The bigger board is from a Thunderbolt dock, and it's at least an 8-layer board with a very heavy copper core for the ground plane. So you really need to crank the exposure in this one. And this kind of imaging would benefit from a slightly different size processing that we'll talk about later. The smaller board is an iPhone board, which is chock full of components, and that also makes it a little bit more challenging to image, but you can definitely see the locations of discrete components and so on.
For heavy pours like this, should we get that Soviet surplus tube I have running? Or
Perhaps that would help, like higher powered X-ray machine with X-ray emitter that goes into hundreds of kilovolts peak would definitely burn through these easily.
There's some point of metal thickness at which the X-rays no longer get through, and that's controlled by your peak voltage, which for the machines that we're using is 35 kilovolts, and we regularly run it at max. So there's not much further to go from max. We can't turn it up to 11.
One more image. When you kind of get a fun toy, you tend to put things in it to image them. These are a pair of Nintendo Joy-Cons. Another example of an image that could have used a little bit more exposure to get more details in the PCB itself, but it shows the mechanical parts quite clearly for potential inspections for breakage or so on. Finally, here's a zoomed-in look at one of the images. This is an SD card that's been imaged on film, but then zoomed-in section of the film. An interesting point here is that although silicon itself is pretty much transparent to X-rays, you can see the bond wires and tell where the die itself is. If you look into both of these chips, you can kind of spot the bond wires. As I mentioned, some of these examples would benefit from a different processing procedure because thicker boards, there's just so much you can do with longer exposures. X-rays themselves scatter, so if you're doing too long of an exposure, you're just raising the noise level as much as the signal, so you're not getting any more details. In my testing, I've tried to use a more aggressive developer. You can control the development process and the results that you get by varying the chemicals and concentrations to boost certain features of the image. Like if you care about the shadow areas, you do one sort of processing, different temperature, different times, and so on. By using a more concentrated solution of the developer, you kind of get a higher contrast from the image, and that helps get the details out of those thicker boards. In this example, I wanted to mention PQ Universal Developer, which is usually used to print photos on paper, but you can also use it for developing film. The dev time is much shorter, which gives you less control, but again, achieve interesting results. That was the first procedure. Second procedure, we wanted to, this is one of the first ideas I kind of had as a simple test, proof of concept that this would actually work. You all know about Polaroids. They're all super fun, but one of the ideas was to test if we could get away with doing X-rays on Polaroids. Because if we could pull it off, you'd have much simpler development procedure, doesn't require any wet chemicals and so on.
Yeah, and a piece of Polaroid film, the handle that you hold it on, that holds the developing chemicals. And the only thing that you need to activate them is basically anything to squish them out so that they hit the rest of the film. I use a bread roller. You can also take apart the mechanism of a camera or use the camera itself, just with no light so that you're not providing a secondary exposure.
So yeah, it's a pretty interesting piece of tech that was developed a long time ago. The chemicals in these pouches are timed, so just as the developer is getting depleted, the fixer is kicking in and doing the exposure. And yeah, the activation thing is just rolling it through these rollers. That's why you see that image from a Polaroid coming out slowly, and that's how you develop the image. In this case, you can either use an actual camera to develop images, or a slightly more practical thing is one of these Instax printers, which does basically the same thing. This is a device that connects to your phone, and you can send photos to it to print on a Polaroid. So we wanted to go through the procedure of developing X-rays on Polaroids, or getting the Polaroid film to work with X-rays. And again, the procedure is relatively similar to prior one. Into the bag or in the dark, you need an X-ray film holder, the same one from before. You need the film pack that contains the slides. You need some sort of a light-tight box to put the rest of the film pack in before you expose it to light, and you need a small flashlight. The flashlight is counterintuitive, but serves a very important purpose. To prepare the film for exposure, you take out the dark slide from the film pack, take one film piece out of the pack and put it and align it in the holder. Then you quickly flash it with light. You do this to put the film over its activation threshold. The Instax film or Polaroid film is special in a way that it's not too sensitive to light, so you need to give it a little bit of initial light to make it essentially more sensitive to X-rays.
So after I've gone to all the trouble of making a dark room, you're telling me to shine a flashlight at my film?
Just a little bit, yeah. You don't want too much, but just a little bit to activate it. Then you put it in the holder, and the rest of the exposure procedure is the same as before. You align it in the machine. You just have to remember that the imaging area is slightly smaller because the sheet of Instax wide film is slightly smaller than the 4x5 film, but it's not too big of an issue. The exposure itself is the same. You issue the same commands. The only difference is in exposure time. You can kind of expect that the exposure time will be longer for Instax film. Here it shows 3 minutes, for example. And once it's exposed, the development is relatively simple. Again, in the dark or in the changing bag, you need to transfer the piece of film that you've exposed to X-rays into the printer, or alternatively, you can use a rolling pin on a sturdy surface to smear those chemicals and kick off the development. And with that, when you put the film in the printer can eject it, it goes through those rollers, and you receive a picture. And then we'll go through a couple of examples of what kind of results you can expect from this. The results themselves are kind of not as high fidelity as you get with the actual black and white film, because the development and the characteristics of Polaroid and Instax film are differently optimized, so they're not as sharp, but you can still kind of get the very interesting results.
This being color film, it also has the nice little side effect of like these crazy little halos around the images. I don't think they serve any practical purpose, but they look really cool.
this also coincidentally answers the question of what color are the X-rays. So apparently they are green or blue. Here's a zoomed-in version of one of the previous photos. Again, shows that same SD card. So if you kind of go back and compare it to the one done on actual film, you can see kind of the loss of detail and in terms of resolution and loss of dynamic range. Where in the previous one, you could see parts of the plastic packaging that's gone here because the film itself isn't as sensitive. But still, interesting. Can give you a pretty quick view of what you're looking at. Another example of a car key card that shows the RFID loop antenna and the location of the chip in case you wanted to do something with that. As Travis mentioned before, car keys or car key fobs are always very interesting to image and makes for a fun party trick, I guess.
Cool. So I hope you enjoyed learning how X-rays work and learning how to jerry-rig a functional one using Darkroom if you get robbed by a sketchy eBay dealer. The other question that keeps coming up is, would it be possible to use the sensor from a digital SLR? Would it be possible to use the sensor from this, from that? As the sensors get even to the 2-inch by 2-inch that the X-ray machine normally uses, they use a lot of surface area from the semiconductor wafer. I really don't believe we're ever going to find a cheap source of 4x5 sensors. If you happen to have a camera with one that you would be willing to sell to me for less than a car, please get in touch.
And if you think about it, in this case, your full-frame digital camera has a 35mm sensor. The biggest commercially produced cameras are medium format cameras, which have maybe 4 times as much surface area. So there aren't really commercially available digital imaging sensors that are accessible to hobbyists, essentially.
So thank you. And I think we now have a minute or two for questions before we get kicked off the stage. Yes?
So a good source for X-rays is medical auction sites. And you can get a lot of good stuff for a lot less than a car. So I got the big boy version of what you've got, which is called a BioVision. It has a 10 by 15 sensor, and I got it from your brand. It has a whole working unit with a cavity.
Okay, so we're going to rob this guy after the show. He has a 10 by 15 sensor. Yes?
When you do the DSLR scanning, are you able to fit it in like one shot, or do you kind of like stitch it together?
So, good question. It comes back to the optics of your DSLR. You can kind of get the zoomed out version and get the full picture. Or if you're really interested in high resolution details of a particular part, you can kind of stitch it together. For the most part, you get the resolution that you get out of it depends on the resolution of the camera, so like 20 megapixels or something. So you can get more if you stitch them together, but in general, you can just take one whole.
Cool. Back there on the right.
Can you put the picture of the mask back up? My kids want to see the picture of the mask.
Is anyone squeamish about mice? Speak now or forever hold your peace. And he's not the mouse. His name is Steamboat Willie. It's legal now. Yes.
Yeah, so you talked about the exposure time on the order of minutes. I was wondering if you knew how long the actual like rated hours for imaging these tubes are good, because they're also kind of right?
So the tubes are not unobtainable. You can import them from Ukraine, and Ukraine really needs hard currency right now. It's basically just a vacuum tube or a light bulb with the wrong build to it so that it makes X-rays instead of visible light. Do you remember that this was invented by accident? There was a regular light bulb that Herr Dr. Röntgen had, and he realized that it was ruining film that he had near the light bulb. So he convinced his wife, Frau Röntgen, to put her hand near it for hours in order to do exposures. She lost her hand doing that, though, so please be very careful with shielding. And one last one, and then I'm afraid we need to leave the stage.
Hey, thanks for the talk. So I've noticed in some of the pictures that you've shared, there's like a yellow sepia tinge. Is that a dye, or is that something you're doing in post-processing?
No, these are completely black and white. That might be the effect of the color in the room, but they are black and white completely.
Oh, I guess it's like some of the pictures that Travis has shared on Twitter, I suppose.
The digital photos?
No, those are black and white. It's like an effect of the projector.
Okay, weird. Thanks.
Otherwise, you get a little bit of color cast from the film base itself, which is kind of purplish, but that's pretty much it.
Cool.
Thanks.
We've got to run. If you have more questions, we'll be upstairs. And if you need a copy of the International Journal of Proof of Concept to get the fuck out, we've got a brand new one for this weekend. There's a whole box at the corner of the stage. Thank you, and have a good evening.